Hey, altruistic well-wishers and constructive critics, I presume that you and your beloved are in a fine figure. Digital activist and good-hearted preacher Professor yesterday is back with altruistic ecstasy for my 101st video on annual of publication on YouTube today, 26th October 2020, Monday, Vijayadashmi. I have selected micro irrigation and smart irrigation for water conservation for presentation today. All of us are aware that edible quality water is a precious commodity that we should make all efforts to conserve it for the future generations. Even though nearly two-thirds of the world is covered by water, hardly 1% of this edible quality, only 1% of this is of edible quality. Rest is saline or breakage. Even though rainwater, when it comes down, is of good quality, most of it is wasted and flows through drains back to sea and gets contaminated. Some efforts are being made to harvest rainwater, but on a low key. Nobody would have ever imagined of paying a high price to purchase edible quality water in households. Now it is a reality even in developed nations like USA, which follows Clean Air, Clean Water Act. In future, countries may start fighting for edible quality water. It is already happening in countries like India, where there is so much enmity between states for sharing of river water. Example, Tamil Nadu and Kerala, Tamil Nadu and Karnataka. About 75% of the edible quality water is consumed by agrarians for farming. 32% is consumed by industry and rest by common men and women for household needs. Irrigation is the process of applying controlled amounts of water to plants at needed intervals. Irrigation helps to grow agricultural crops, mainly maintain landscapes and revegetate disturbed soils in dry areas and during periods of less than average rainfall. Irrigation also has other uses in crop protection, including frost protection, suppressing weed growth in grain fields, and preventing soil consolidation. In contrast, agriculture that relies only on direct rainfall is referred to as rain-fed. Irrigation systems are also used for cooling livestock, dust suppression, disposal of sewage, and in mining. Irrigation is often studied together with the drainage, which is also the removal of surface and subsurface water from a given area. Irrigation has been a central feature of agriculture for over 5,000 years and is a product of many cultures. Historically, it was the basis for economies and societies around across the world, from Asia to the southwestern US. In ancient civilizations, people used to live beside water sources like rivers, streams, ponds, etc. Archaeological investigation has found evidence of irrigation in areas lacking sufficient natural rainfall to support crops for rain-fed agriculture. The most common use of technology dates back to the 6th millennium BCE in Khuzestan in the southwest of present-day Iran. Irrigation was used as a means of manipulation of water in the alluvial plains of the Indus Valley civilization. Indus Valley. Application of it is estimated to have begun around 4500 BC and drastically increased the size and prosperity of the agricultural settlements. The Indus Valley civilization developed sophisticated irrigation and water storage systems, including artificial reservoirs at Girnar dated to 3000 BCE and the yearly canal irrigation system from c. 2600 BCE. Large-scale agriculture was practiced with an extensive network of canals used for the purpose of irrigation. Farmers in the Mesopotamian plain used irrigation from at least the 3rd millennium BCE. They developed perennial irrigation, regularly watering crops through the growing season by coaxing water through a matrix of small channels formed in the field. Ancient Egyptians practiced basin irrigation using the flooding of the Nile to inundate land plots which had been surrounded by dikes. The floodwater remained until the fertile sediment had settled before the engineers returned the surplus to the watercourse. There is evidence that ancient Egyptian Pharaoh Amenemhet III in the 12th dynasty, about 1800 BCE, used the natural lake of the Fayum oasis as a reservoir to store surpluses of water for use during dry seasons. The lakes filled annually from the flooding of the Nile. The ancient Nubians developed a form of irrigation by using a water wheel-like device called a sakia. Irrigation began in Nubia sometimes between the 3rd and 2nd millennia BCE. It largely depended upon the floodwaters that would flow through the Nile River and other rivers in what is now the Sudan. In sub-Saharan Africa, irrigation reached the Niger River region cultures and civilizations by the 1st or 2nd millennium BCE and was based on wet season flooding and water harvesting. Evidence of terrace irrigation occurs in pre-Columbian America, early Syria, India, and China. In the Zana Valley of the Andes Mountains in Peru, archaeologists have found remains of three irrigation canals radiocarbon dated from the 4th millennium BCE, the 3rd millennium BCE, and the 9th century CE. These canals provide the earliest record of irrigation in the New World. Traces of a canal, possibly dating back from the 5th millennium BCE, were found under the 4th millennium canal. Ancient Persia, modern-day Iran, used irrigation as far back as the 6th millennium BCE to grow barley in areas with insufficient natural rainfall, arid regions. The Quants Quanax, developed in ancient Persia about 800 BC, are among the oldest known irrigation methods still in use today. They are found in Asia, the Middle East, and North Africa. The system comprises a network of vertical wells and gently sloping tunnels driven into the sides of cliffs and of steep hills to tap groundwater. The Noria, a water wheel with clay pots around the rim powered by the flow of the stream or by animals where the water source was still, first came into use at about this time among Roman settlers in North Africa. By 150 BCE, the pots were fitted with valves to allow smoother filling as they were forced into the water. In the year 2000, the total fertile land was 2. No, 2,788,000 square kilometer, which is equivalent to 689 million acres, and it was equipped with irrigation infrastructure worldwide. About 68% of this area is in Asia, 17% is in the Americas, 9% in Europe, 5% in Africa, and 1% in Oceania. The largest contiguous areas of high irrigation density are found in northern India and Pakistan along the Ganges and the Indus rivers, in the Hai-He, Wang-He, and Yangtze basins in China, along the Nile River in Egypt and Sudan, in the Mississippi-Missouri River Basin, the southern Great Plains, and in parts of California, US. Smaller irrigation areas are spread across almost all populated parts of the world. There are several methods of irrigation. They vary in how the water is supplied to the plants. The goal is to apply supply the water to the plants as uniformly as possible, so that each plant has an amount of water it needs, neither too much nor too little. Surface irrigation is the oldest form of irrigation and has been in use for thousands of years. In surface, flood or level basin irrigation systems, water moves across a strip across the surface of agricultural lands in order to wet it and infiltrate into the soil. Surface irrigation can be subdivided into furrow, border strip, or basin irrigation. It is often called flood irrigation when the irrigation results in flooding or near flooding of the cultivated land. Historically, this has been the most common method of irrigating agricultural land and is still used in most parts of the world. It is conventional, traditional, where water levels from the irrigation source permit. The levels are controlled by dikes, usually dug by soil. This is often seen in terraced rice fields, rice paddies, where the method is used to flood or control the level of water in each distinct field. In some cases, the water is pumped or lifted by human or animal power to the level of the land. The water application efficiency of surface irrigation is typically lower than other forms of irrigation. Surface irrigation is even used to water landscapes in certain areas, for example, in and around Phoenix, Arizona, US. The irrigated area is surrounded by a berm and the water is delivered according to a schedule set by local irrigation district. Micro irrigation, sometimes called localized irrigation, low volume irrigation, or trickle irrigation, is a system where water is distributed under low pressure through a pipe network in a predetermined pattern and applied as a small discharge to each plant or adjacent to it. Traditional drip irrigation systems use individual emitters. Subsurface drip irrigation (SDI), micro spray, micro sprinklers, and mini bubbler irrigation all belong to this category of irrigation methods. Drip or micro irrigation, also known as trickle irrigation, functions as its name suggests. In this system, water falls drop by drop just at the position of the roots. Water is delivered at or near the root zone of plants drop by drop. This method can be most water efficient method of irrigation, drip irrigation. If managed properly, evaporation and runoff are minimized. The field water efficiency of drip irrigation is typically in the range of 80 to 90% when managed correctly. In modern agriculture, drip irrigation is often combined with plastic mulch, further reducing evaporation, and is also the means of delivery of fertilizer. The process is known as fertigation. Deep percolation, where water moves below the root zone, can occur if a drip system is operated for too long or if the delivery rate is too high. Drip irrigation methods range from very high-tech and computerized to low-tech and labor-intensive. Lower water pressures are usually needed than for most other types of systems, with the exception of low-energy center pivot systems and surface irrigation systems, and the system can be designed for uniformity throughout the field or for precise water delivery to individual plants in landscape containing a mix of plant species. Although it is difficult to regulate pressure on steep slopes, pressure compensating emitters are available, so the field does not have to be level. High-tech solutions involve precisely calibrated emitters located along lines of tubing that extend from a computerized set of valves. In sprinkler or overhead irrigation, water is piped to one or more central locations within the field and distributed by overhead high-pressure sprinklers or guns. A system using sprinklers, sprays, or guns mounted overhead or permanently installed risers is often referred to as a solid set irrigation system. Higher pressure sprinklers that rotate are called rotors. and are driven by a ball drive, gear drive, or impact mechanism. Rotors can be designed to rotate in a full or partial circle. Guns are similar to rotors, except that they generally operate at very high pressures of 275 to 900 kilopascals, which is equivalent to 40 to 130 psi, pounds per square inch, and flows to 3 to 76 liters per second, which is equivalent to 50 to 1200 US gallons per minute, usually with the nozzle diameters in the range of 10 to 50 mm, 50, 0.5 to which is equivalent to 0.5 to 1.9 inches. Guns are used not only for irrigation but also for industrial applications such as dust suppression and logging. Sprinklers can also be mounted on moving platforms connected to the water source by a hose. Automatically moving wheel systems known as traveling sprinklers may irrigate areas such as small farms, sports fields, parks, pastures, and cemeteries unattended. Most of these use a length of polyethylene tube wound on a steel drum. As the tubing is wound on the drum powered by the irrigation, water, or a small gas engine, the sprinkler is pulled across the field. When the sprinkler arrives back at the reel, the system shuts off. This type of system is known to most people as a water reel. Traveling irrigation sprinkler, and they are used extensively for dust suppression, irrigation, and land application of wastewater. Other travelers use a flat rubber hose that is dragged along behind when the sprinkler platform is pulled by a cable. Center pivot irrigation is a form of sprinkler irrigation utilizing several segments of pipe, usually galvanized steel or aluminum, joined together and supported by trusses mounted on wheeled towers with the sprinklers positioned along its length. The system moves in a circular pattern and is fed by water with the water from the pivot point at the center of the arc. These systems are found and used in all parts of the world and allow irrigation for all types of terrain. Newer systems have drop sprinkler heads as shown in the newer systems have drop sprinkler heads. As of 2017, the most center pivot systems have drops hanging from a U-shaped pipe attached at the top of the pipe and the sprinkler heads that are positioned at a few feet at most above the crop, thus limiting evaporative losses. Drops can also be used with the drag hoses or bubblers that deposit the water directly on the ground between crops. Crops are often planted in a circle to conform to the center pivot. This type of system is known as low energy precision application, shortly LEPA. Originally, most center pivots are water powered. These are replaced by hydraulic systems, fuel irrigation, and electric motor-driven systems. Many modern pivots feature GPS devices, global positioning system devices. A launch sprinkler system is permanently installed as opposed to a hose-end sprinkler, which is portable. Sprinkler systems are installed in residential lawns, in commercial landscapes for churches and schools, in public parks and cemeteries, and on golf courses. Most of the components of these irrigation systems are, are hidden underground, since aesthetics are important in a landscape. A typical lawn sprinkler system will consist of one or more zones limited in size by the capacity of the water source. Each zone will cover a designated portion of the landscape. Sections of the landscape will usually be divided by a microclimate, type of plant material, and type of irrigation equipment. The landscape irrigation system may also include zones containing drip irrigation, bubblers, or other types of equipment besides sprinklers. Although manual systems are still used, most lawn sprinkler systems may be operated automatically using an irrigation controller, sometimes called a clock or timer. Most automatic systems employ electric solenoid valves. Each zone has one or more of these valves that are wired to the controller. And the controller sends power to the valve opens, allowing water to flow to the sprinklers in that zone. There are two main types of sprinklers used in lawn irrigation: pop-up spray heads and rotors. Spray heads have a fixed spray pattern, while rotors have one or more streams that rotate. Spray heads are used to cover smaller areas, while rotors are used for larger areas. Golf course rotors are sometimes so large that a single sprinkler is combined with a valve and called a valve in head. When used in a turf area, the sprinklers are installed with the top of the head flush with the ground surface. When the system is pressurized, the head will pop up out of the ground and water the desired area until the valve closes and shuts off the zone. Once there is no more pressure in the lateral line, the sprinkler head will retract back into the ground. In flower bed or shrub areas, sprinklers may be mounted on above ground risers or even taller pop-up sprinklers may be used and installed flush as in a lawn area. There are many types of hose-in sprinklers. Most of them are smaller versions of large agricultural and landscape sprinklers sized to work with the typical garden hose. Some have a spiked base, allowing them to be temporarily stuck in the ground, while others have a straight base designed to be dragged while attached to the hose. Sub-irrigation has been used for many years in field crops in areas with high water tables. It's a method of artificially raising the water table to allow the soil to be moistened from below the plant's root zone. Often those systems are located on permanent grasslands in lowlands or river valleys and combined with the drainage and infrastructure. A system of pumping stations, canals, weirs, and gates allows it to increase or decrease the water level in the network of ditches and thereby control the water table. Sub-irrigation is also used in the commercial greenhouse production, usually for potted plants. Water is delivered from below, absorbed by upwards, and the excess controlled by for recycling. Typically, a solution of water and nutrients floods a container or flows through a trough for a short period of time, 10 to 20 minutes, and is then pumped back into a holding tank for reuse. Sub-irrigation in greenhouses requires fairly sophisticated, expensive equipment and management. Advantages are water and nutrient conservation and labor savings through reduced system maintenance and automation. It is similar in principle and action to subsurface basin irrigation. Another type of sub-irrigation is a self-watering container, also known as a sub-irrigated planter. This consists of a planter suspended over a reservoir with some type of wicking material such as a polyester rope. The water is drawn up the wick through capillary action. A similar technique is a wicking hybrid. These two uses capillary action. Subsurface textile irrigation, shortly SSTI, is a technology designed specifically for sub-irrigation in all soil textures from desert lands to heavy clays. A typical SSTI system is an impermeable base layer, usually polyethylene or polypropylene, a drip line running along the base, a layer of geotextile on top of the drip line, and finally a narrow impermeable layer on top of the geotextile. Unlike standard drip irrigation, the spacing of emitters in the drip zone pipe is not critical as the geotextile moves the water along the fabric up to 2 meters from the drip. The impermeable layer effectively creates an artificial water table. Irrigation water can come from groundwater extracted from springs or by using wells, from surface water withdrawn from rivers, lakes, or reservoirs, or from non-conventional sources like treated wastewater, desalinated water, drainage water, or fog collection. A special form of irrigation using surface water is spade irrigation, also called floodwater irrigation. In case of a flood, spade water is diverted to normally dry river bodies using a network of dams, gates, and channels and spread over large areas. And moisture stored in the soil will be used thereafter to grow the crops. Spade irrigation areas are in particular located in semi-arid or arid mountainous regions, while floodwater harvesting belongs to the accepted irrigation methods. Rainwater harvesting is usually not considered as a form of irrigation. Rainwater harvesting is a collection of runoff water from roofs or unused land, and the concentration of this, around 90% of wastewater produced globally, remains untreated, causing widespread water pollution. Especially in low-income countries, especially increasingly agriculture uses untreated wastewater as a source of irrigation water. Cities provide lucrative markets for fresh produce or attractive to farmers. However, because the agriculture has to compete for increasingly scarce water resources with industry and municipal users, there is often no alternative for farmers but to use water polluted urban waste, including sewage, directly to water their crops. It is happening in major cities or metros. Significant health hazards can result from using water loaded with pathogens in this way, especially if people eat raw vegetables that have been irrigated with the polluted water. The International Water Management Institute has worked in India, Pakistan, Vietnam, Ghana, Ethiopia, Mexico, and other countries on various projects aimed at assessing and reducing risks of wastewater irrigation. They advocate a multiple barrier approach to wastewater use where farmers are encouraged to adopt various risk reducing behaviors. These include ceasing irrigation a few days before harvesting to allow pathogens to die off in the sunlight, applying water carefully so it does not contaminate leaves likely to be eaten raw, cleaning vegetables with the disinfectant, or allowing fecal sludge used in farming to dry before being used as human manure. The World Health Organization (WHO) has developed guidelines for safe water use. In countries where humid air sweeps through at night, water can be obtained by condensation onto cold surfaces. This is practiced in the vineyards of Lanzarote using stones to condense water. Fog collectors are also made of canvas or foil sheets. Using condensate from air conditioning units as a water source is becoming more popular in large urban areas. As of November 2019, a Glasgow-based startup has helped a farmer in Scotland to establish edible salt marsh crops irrigated with the seawater. An acre of previously marginal land has been put under cultivation to grow samphire, sea blight, and sea aster. These plants yield a good higher profit than potatoes. The land is flood irrigated twice a day to simulate tidal flooding. Water is pumped from the sea using wind power. Additional benefits are soil remediation and carbon sequestration. Successful agriculture is dependent upon farmers having sufficient access to water. However, water scarcity is already a critical constraint to farming in many parts of the world. With regards to agriculture, the World Bank targets food production and water management as an increasingly global issue that is fostering a growing debate. Physical water scarcity is where there is not enough water to meet all demands, including that needed for ecosystems to function effectively. Arid regions frequently suffer from physical water scarcity. It also occurs where water seems abundant but where resources are overcommitted. This can happen where there is overdevelopment of hydraulic infrastructure, usually the irrigation. Symptoms of physical water scarcity include environmental degradation and declining groundwater. Economic scarcity, meanwhile, is caused by a lack of investment in water or insufficient human capacity to satisfy the demand for water. Symptoms of economic water scarcity include a lack of infrastructure, with people often having to fetch water from rivers for domestic and agricultural uses. Some 2.58 billion people currently live in water scarce areas. Irrigation schemes involve solving numerous engineering and economic problems while minimizing negative environmental consequences. Such problems include competition for surface water rights, overdrafting, depletion of underground aquifers. The mid 20th century advent of diesel and electric motors led to systems that could pump groundwater out of major aquifers faster than drainage basins could refill them. This can lead to permanent loss of aquifer capacity, decreased water quality, ground subsidence, and other problems. The future of food production in such areas as the North China Plain, the Punjab, and the Great Plains of the US is threatened by this phenomenon. Ground subsidence, under irrigation or irrigation giving only just enough water for the plant. Example, in drip line irrigation gives poor soil salinity control, which leads to increased soil salinity and consequent buildup of toxic salts on soil surface in areas with high evaporation. This requires either leaching to remove these salts and a method of drainage to carry the salts away. When using a drip lines, leaching is best done regularly at certain intervals with only a slight excess of water, so the salt is flushed back under the plant's roots. Drainage front instability, also known as viscous fingering, where an unstable drainage front results in a pattern of fingers and viscous entrapped saturated zones. Over irrigation, because of poor distribution uniformity or management wastewater chemicals, and may lead to water pollution. Deep drainage from over irrigation may result in rising water tables, which in some instances will lead to problems of irrigation salinity, requiring water table control by some form of subsurface land drainage. Irrigation with the saline or high sodium water, they damage soil structure owing to the formation of alkaline soil. Clogging of filters, it is mostly algae that clogs filters, drip installations and nozzles. Ultraviolet and ultrasonic methods can be used for algae control in irrigation systems. Assisting smallholders is sustainably assisting smallholders in sustainably and collectively managing irrigation technology and changes in technology. The 2016 found that countries whose agriculture depended on irrigation are more likely to be autocratic than other countries. The authors of the study argue that the effects of as historical origins, irrigation allowed landed elites in arid areas to monopolize water and arable land. This made elites more powerful and better able to oppose democratization. Micro irrigation, also called as localized irrigation, low volume irrigation, low flood irrigation, or trickle irrigation, is an irrigation method with lower pressure and flow than a traditional sprinkler system. Low volume irrigation is used in agriculture for row crops, orchards, and vineyards. It's also used in horticulture, in wholesale nurseries, in landscaping for civic, commercial, and private landscapes and gardens, and in the science and practice of restoration ecology and environmental remediation. The lower volume allows the water to be absorbed into slow percolation soils such as clay, minimizing runoff. The low flow irrigation systems are used in native plant habitat restoration and environmental remediation projects. The lower operating pressure can be the only choice for remote locations with wells or small storage tank water sources. It is used in temporary installations during initial establishment periods and when the soil surface is easily removable with minimal damage to the recovering plant community. An example is its use in riparian zone restoration and environmental remediation projects using phytoremediation and bioremediation techniques. As municipal and agricultural water supplies have become more constrained due to increasing population, droughts, and climate change, city, water district, and state province level regulations and codes are beginning to encourage or mandate reduced water consumption. Use of micro irrigation systems on green building green building candidate projects can help them to accumulate points for leadership in energy and environmental design LEED certification, rating, and awards. Real-time monitoring of temperature, moisture, humidity, and nutrient facts of soil and atmosphere can correctly guide the agriculture and improve crop production. Precision agriculture is an agricultural system that can contribute to the sustainable agricultural concepts. If installed and programmed properly, automatic agricultural systems can save money and help in water conservation. Automatic agricultural systems can be programmed to discharge more precise amounts of water in the field, which promotes water conservation. At present, labor saving and water saving technology is a key issue in agriculture. There have not been any significant technological advancements made in agricultural sector as compared to other sectors. Agricultural system needs to be monitored on a regular basis. With the help of solar energy, the power need is satisfied. The added feature is the happenings in the farm are sent through a message to farm owner and the nutrient details to the server at regular intervals to improve soil quality. The system components of server, which are microcontroller processed with embedded sensors measuring different parameters. Here the server contains all the details of the particular locality, say nutrient content of the soil, moisture, and other factors. With the help of the data, authorities can teach the farmers to plant the apt crop at the right time and get the maximum yield. Sustainable growth is established. Work of sensors is to sense the moisture, temperature, and humidity. Smart irrigation systems that optimize the available water in the water reservoir, thus providing an efficient and effective water usage solution for the irrigation system. Irrigation system is able to automatically start or stop water pumps on the irrigation side based on the soil moisture content acquired from the moisture content sensor as well as the ultrasonic sensor measuring the water level in the reservoir. The measured sensor values are sent to the Arduino microcontroller for configuring the control algorithm. The system prioritizes Prioritizes irrigation operation by determining the number of pumps to be operated at any instance as well as the location. In this way, different crops can be watered depending on their varying water requirements. In order to implement the design, a laboratory-scale architectural model depicting a farm setting with a reservoir, direct current pumps, and the control unit was constructed. Experimental results reveal good performance, which makes the developed system a suitable tool for studies on irrigation. A substantial amount of water is lost to evaporation, wind, and runoff as a consequence of improper watering methods. Even watering of plants should be done either early morning or late in the evening, not when the temperature is very high during daytime. When the sun is out. Reducing or eliminating these loss decreases utility bills and creates a more water efficient, healthy landscape. Outdoor water savings can be achieved using smart irrigation technology. Smart irrigation controllers and sensors have been developed to reduce outdoor water use by irrigating based on plant water and plant water need compared to traditional automatic system timers which irrigate on a user-determined fixed schedule. This technology exists as a complete controller or as a sensor that can be added to an existing irrigation timer to create a smart controller. Smart irrigation technology uses weather data or soil moisture data to determine the irrigation need of the landscape. There is a broad spectrum of smart irrigation technologies that consumers can benefit from utilizing. Choosing the correct technology for the situation is essential to achieve potential water savings. Climate-based controllers, also referred as evapotranspiration (ET) controllers, use local weather data to adjust irrigation schedule. ET is a combination of evaporation from the soil surface, and transpiration by plant materials. These climate-based controllers gather local weather information and make irrigation runtime adjustments so the landscape only receives the appropriate amount of water. There are three basic types of ET controllers. Signal-based controllers use meteorological data from a publicly available source, and the ET value is calculated from a glass surface of the sun. The ET data is then sent to the controller by a wireless connection. Historic ET controllers use a pre-programmed water use curve based on historical water use in different regions. The curve can be adjusted for temperature and solar radiation. On-site weather measurement controllers use weather data collected on-site to calculate continuous ET measurements and water accordingly. ET controllers have been shown to reduce outdoor water use. Second type of smart irrigation controllers include soil moisture sensor controllers. Instead of using weather data, soil moisture sensor controllers utilize the soil moisture sensor placed below ground in the root zone of lawns to determine the water need. Soil moisture sensor estimates the soil volumetric water content. Volumetric water content represents a portion of the total volume of soil occupied by water. The controllers can be adjusted to open the valves and start irrigation once the volumetric water content reaches a user-defined threshold. The appropriate threshold value depends on soil and vegetation type and usually ranges from about 10 to 40%. Soil moisture sensors must be installed in a representative area of the turf, far enough from sprinkler heads. Tree roads, sidewalks, and walls. Similar to ED controllers, soil moisture controllers have been shown to reduce irrigation while maintaining grass quality. Compared to home owner irrigation schedules, soil moisture controllers had an average 72% irrigation savings and a 34% water savings during drought. In some cases, studies have shown smart controllers will increase water use at sites that typically use less than the theoretical irrigation requirement. In many cases, the scheduling irrigation control is already in use on a property and upgrading to a smart controller is impractical. Increase efficiency of automatic irrigation systems. Soil moisture, rain, wind or freeze sensor can be added to upgrade the existing system. Some manufacturers produce devices capable of measuring multiple environmental elements using one apparatus. Many sensors are compatible to existing systems, easy to install and produce similar results to smart irrigation controllers. Add-on sensors are generally more affordable than smart irrigation controllers. Assuming a compatible irrigation timer is already installed on site. Soil moisture sensors can be connected to the existing irrigation system controller. The sensor measures the soil moisture content in the root zone before a scheduled irrigation event and bypasses the cycle if the soil moisture is above a specific threshold. Different types of soil moisture sensors are available, and the consumer should ensure system compatibility before purchasing the sensor. It should be appropriate. Some soil moisture sensors include a soil freeze sensor that will interrupt the irrigation cycle if temperatures fall below 32 degrees Fahrenheit. Soil moisture sensors are available as wired or wireless systems. Rain and freeze system sensors interrupt the irrigation cycle during a rain or freeze event when irrigation is unnecessary. Watering during the rain causes waste, water, money, and causes unnecessary runoff or flooding also. State. Three different types of rain sensors are available. Each function is based on separate concepts. They need to be replaced. All of the devices should be mounted in an open area where they will receive rainfall. Potential water savings depends on the amount of rainfall in any given year. During years with average to above average rainfall, water savings are more significant than during dry years. Rain sensors have shown payback periods of less than a year but should be monitored for optimum performance. Freeze sensors interrupt an irrigation cycle when air temperatures fall below 32 degrees Fahrenheit, that is 0 degrees Celsius. Eliminating irrigation during freezing temperatures can potentially increase irrigation system life and prevent sidewalks and streets from icing over, causing dangerous situations. Many rain sensors include a freeze sensor, and homeowners should account for sensor capability when considering the price. Smart irrigation technology may help reduce water wastage while also providing a healthy, attractive landscape. Irrigation system owners should provide regular maintenance and ensure the irrigation system is only watering the landscape when needed. In 21st century, the term smart is used for anything and everything, like smartphones, smart TV, smart homes, smart vehicles, smart lights, light bulbs, smart plugs. As a matter of fact, I got a smart plug today. It's basically, it will cut off the power supply to the equipment that is connected to it when the voltage is too low or too high, and it can withstand up to 4,000 volts, I guess. It has spread to irrigation too. Basically, smart means using sensors and controllers for the equipment system, etc. People need to be smart rather than the aids we use, but people have become dumb and dumber with the advancement in technology, and ultimately, technology will control everything, including humans. Technology make become the master, and humans slaves are annihilated forever, eliminated. Those days are not far off. We should utilize the technology for our benefit, but at the same time, exercise adequate caution to ensure that they never take the upper hand. To mitigate water scarcity, seawater desalination is an option, but right now it is not a viable solution since it's not cost effective. Saudi Arabia is the biggest seawater desalination plant in the world. Governments need to spend more on research and development activities, especially development of cost-effective technology for seawater desalination and water recycling plants, which would benefit humans all over the world forever, since we'll never run out of seawater. Developed countries are spending so much money on unwanted research, like the sound made by the bee when it mates and all that. What is the necessity for that? Or sending space satellites into space to collect so much unwanted data or spying and all that. Use the money for constructive purposes rather than for destruction. Construction is tougher, destruction is easy. Debates, discussion on open-ended topics like this can go on forever. Anyway, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements used expressed are solely mine based on limited knowledge gained over 6 decades of versatile experience. Always watch these videos with closed captions, subtitles for absolute 100% comprehension as per my sincere recommendation. Zillion times so far. I know I rushed through to complete the presentation within 20 minutes max, which is a norm that I admit set myself to retain the viewer's attention. But of course, nowadays I exceed this time limit since I make honest attempts to cover the selected topic, including more elaborately, including so many intricate fine details, referring a wide variety of sources, in particular Wikipedia quite extensively, besides articles and books published recently. I am also gaining knowledge. I need to admit that. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay at home as much as possible to maintain social distancing attributed to pandemic novel COVID-19 and prolong your lifespan. Lead a healthy life and not a filthy life. God alone can put a stop to natural and unnatural events, maybe bio and cyber war events like pandemics, which may lead to apocalypse and extinction of all sentient species on earth for no fault of others. Rest in peace and harmony.